This is an explanation of how to use the walk-up NMR system. So when you come to the instrument, it should already have top spin, which is the main NMR program running. It should have the lock display open, and it should have the icon NMR window open here like this. If these are not open, you can get to them. I'll show you how to get back to this point in case the instrument's not in this state. So if the computer were to be rebooted, it comes up with a login screen. The username and password are indicated here on these troubleshooting sheets. So log in with the username and password. And then you can click on the top spin icon to start the top spin program, which is the main NMR program. You can go to spectrometer, icon NMR, main screen to start icon NMR. And then you can click on this button here, which is the lock display, to start the lock display. So now we're back to the way the instrument should be when you first start to use it, and when you're finished using it, it should be back in this state. Okay, so the next thing to do is to log in, and we use the automation system whether or not we're using a sample changer, just to keep the interface consistent. So on the instruments that you're using manually without the sample changer, you'll need to log into the automation by clicking on this icon here, and then put in your username and password. You'll see this screen show up. It has a whole series of holders listed on the side here. The purpose for these holders is for the sample changer. So a sample changer, for example, might have holders 1 through 60, which means that if you put your sample in that holder on the sample changer, then it will know what experiment to run on that sample. Now, using it manually, you don't need all these holders, but they're still useful because they allow you to distinguish different samples from each other. So if you came down to use the instrument with 2 different samples, you can add them to 2 separate holders. To do that, you can either double-click, or you can highlight and click the Add button to add experiments to different holders. So this would indicate that you wanted to run whatever this experiment is, which we haven't defined yet, on this sample, and some other experiment on another sample. If you add multiple experiments to the same holder, this tells the instrument that you want to run multiple different experiments on the same sample. So for example, say you wanted to run a proton, a cozy, and a carbon all on the same sample, you could put them all in the same holder. If you wanted to run protons on multiple samples, you can put them in separate holders. The main thing is that if they're all in the same holder, as soon as it finishes the first experiment, it will immediately start the next experiment with no additional setup. When it goes from one holder to the next, it will go through all the setup procedures again. So changing the sample, logging, and shimming. So you could run it on the same sample on different holders, but you'd be wasting your time. If you add experiments that you don't mean to, you can get rid of them by highlighting and clicking the delete button. Now, as you add the experiments, it automatically makes a folder with the instrument, the date, and your username, and then it numbers all the experiments that you run on that day. The numbers go by 10s for different samples, and they go by 1s for different experiments on the same sample. We're just going to run a single proton, so we just need this one template here. So the next thing to do is fill in the empty boxes. So the first thing we need to fill in is the solvent. All of the reasonable solvents should be in the list, so I am going to choose chloroform, which is one of the most common ones. Then choose the experiment. Most of the common experiments will be at the top of the list. There's a lot of experiments in the list. I've left any experiment that could conceivably be run on the instrument in the list, but that doesn't mean just because it's in the list that it's a good experiment to run. If you don't know what the experiment is, it'd be a good idea to talk to Instrument Center staff prior to running the experiment. At the top of the list on all of the NMR spectrometers is protons. This one is a carbon detect experiment with proton decoupling. This one is an attached proton test. It's a carbon with a delay inserted that causes CH and CH3 carbons to be phased positively and CH2 and quaternary carbons to be phased negatively. That's very similar to the type of data you'll get from a DEPT, which is a different pulse sequence. And the main thing that's different with a DEPT is that you will get slightly more signal to noise and you will not see any quaternary carbons. This is a fluorine experiment here. The only instruments that can run fluorine are the B400B, the V300A, and the V300B. This is phosphorus. So for example, on one of the other instruments that cannot run fluorine, this should not be in the list. Below here, there's more advanced experiments. Some of them require additional setup. So the main thing is, if you don't know what the experiment does, please talk to Instrument Center staff to get a good idea of what you should use it for and the best way to set it up prior to running it. But for just a standard proton, we can just pick the experiment from the list. If you want to customize some of the common parameters, you can click on this blue and yellow box right here, and you can edit some of the main parameters. D1 is the delay between scans. This allows the spins to relax after they've been pulsed. If you want to be more quantitative with your experiment, you may want to increase this delay. However, to know the proper setting for this, you should know the T1 of your protons. Typically, to be more quantitative, you're going to need to be on the order of like 10 seconds per scan for a small molecule. 1 second is a good number to get data in reasonably quickly without saturating the signals. NS is the number of scans. We almost always do signal averaging in NMR. This improves signal to noise and allows us to do phase cycling, which cancels out some artifacts and external noise that may come into the system. So to do phase cycling, you want to make sure that NS is at least a multiple of 4. And the safest bet is to make NS a power of 2. So we could change this to be, for example, 32 or 64. And just remember that the number of scans will improve the signal to noise, but only with the square root of the number of scans. So if you want 10 times more signal to noise, you need 100 times more scans. So more scans is not a complete substitute for more sample. If you change the number of scans and then click OK, it will update and tell you how long the experiment is going to take. So if you want to run the experiment within a specified time, you can adjust the number of scans and try to fit it within the amount of time that you have available. The default for a proton is 16. That gives a reasonable signal to noise and good phase cycling. DS is dummy scans. That's a couple of scans that it throws away at the beginning of the experiment. This is helpful for phase cycling because you want to make sure that the spectrum is being acquired at steady state. So the first couple of scans might be different from the later ones, so we typically throw them away. O1P is the offset in parts per million. This is the center of the spectrum in parts per million. On some experiments, you may need to change this in order to see signals that are outside the normal range or to irradiate a particular peak. O2P is the offset of the second channel. For a proton, this has no meaning, but for other experiments, for example, carbon, you'll see that O1P is the center of the carbon channel, and O2P is where the proton decoupler is set. You can also see that when you choose different experiments, it populates the parameter field with reasonable values for that experiment. So if you, don't have an idea of how these parameters should be set, you can probably stick with the defaults and have a reasonably good data set. Okay, we're just going to run the default proton with all of the settings the way they are. Last thing is this title box. This is the best way to indicate what your sample is. You can put multiple lines of text in there if you want. It's better to indicate the what your sample is in this title box rather than trying to edit the name over here. The reason is this name is saved directly to the disk, And if you put in spaces or other characters that are not friendly with the Linux operating system, it can screw up the software. So unless you really know what you're doing, I recommend that you leave this alone and put all your identifying information in here. Okay, so once you've added the experiment, chosen the solvent, the experiment, the parameters, and the title, the next step is to click Submit. This changes the status to being queued. That tells the instrument that you want to run the experiment. On the sample changer, this is actually the last step that you need to do. You can just make sure that your sample is in the correct holder, the right experiment is queued, and then you can wait for it to automatically run. On the other instruments, the other walk-up instruments, there's another couple steps you need to do to actually tell the instrument that you want to run it. So what you need to do after you queue the experiment is go up to this Run menu here and tell it that you want to do a new run. You'll also notice that there's an item here in the menu for manual lock and shim. If it's disabled, like it's showing right here, that means that it's not going to do manual lock and shim. That means it's going to do automatic lock and shim, which is fine. But if you want to manually lock and shim, make sure that it's enabled, the yellow box, before you start your run. So I'll leave it enabled so you can see how that works, but it's your choice whether you do it manually or automatically. So we will click New Run. This window pops up, and unless you're doing a more advanced experiment like variable temperature or something like that, you can just click Start. And then the next step you'll see is a window will pop up that says click here to start eject routine. So you can click OK. That will turn on the eject air. And you can go over to the magnet. Now before you go over to the magnet, it's a good idea to remove your wallet and anything else that you might think could be harmed by a strong magnetic field. The 400s are shielded magnets, so it's not quite as critical, but some of the higher field instruments are not shielded, so they could erase your credit cards or damage a cell phone or other electronics. So we're going to go over to the instrument. One rule we have on all the walk-up instruments is that we always keep a dummy sample inside of the magnet. Purpose for this is to make sure that we don't try to put two samples in the magnet. So that means that when you click eject, if nothing pops up, don't assume that the instrument is empty. Assume that there's a sample stuck down inside the magnet. The worst thing that you can do, maybe not the worst, but a bad thing that you could do, is to drop another sample in on top of a sample that's already in there. It could break, make a mess, and be no good. In this case, the sample popped up, so that's good. If nothing popped up, the best course of action is to contact Instrument Center staff, and if you can't find them, leave a note on the report a problem link on the website. The dummy sample is just a tube of D2O, it's just a placeholder, and we're going to trade it out with our sample. So we'll go back over here, get our sample. You should know how to properly prepare your sample. It needs to be a reasonable height and in a good NMR tube. If the sample is too short, or if the tube is bad, or if there is debris in your sample, all of these things will cause poor resolution in your sample, and you'll get bad data. In this case, a reasonable height is typically 500 to 600 microliters. 600 is probably a good rule of thumb to use. You'll want to put it in the spinner, put the sample in the depth gauge, and push it down to the bottom. Now, if your sample is a little bit short, you may not want to push it all the way to the bottom, but rather center it on this center line right here. The reason for that is the only part of the sample that's being detected is this black bar here where it says receiver coil. It's a 5mm tube. This black bar here is the part of the sample that's actually being observed. Now you might say, well, then I don't need the remaining parts of the sample. The reason you need the remaining parts of the sample extending above and below is when you put the sample into the magnetic field, the sample itself distorts the magnetic field. That distortion is fairly uniform in the middle, but it curves around kind of like a bar magnet on the ends. We need the ends to be far away from the part that we're observing, so that's why the sample needs to be taller than the part that we're observing. Now, because we're only observing this part, if you made your sample really tall, you're not going to get any more signal than if it's a reasonable height. So there's no point in having too tall of a sample either. Once your sample is reasonable height, correct depth, maybe a good idea to wipe down the outside of the sample to make sure that there's no dirt or debris on the outside of the tube. You can take it up here and put it into the magnet. It should float on top of the magnet. And then you can come back to the computer. And basically you can follow the instructions here. So it says, please insert your new sample on top of the magnet while the lift is on. Click here when finished. So we've done that. We can click OK. Now if you've chosen automatic lock, automatic shim, then you can just sit back and wait, and it should take it through all of the steps. You can watch the little icons, that's why it's called Icon NMR, flashing as it does each of the steps. So the first step that it's doing is it's spinning the sample. You can look at the panel over here to see if the light is flashing, that means it's trying to spin, but it's not at the right spinning speed. Once it gets to the right spinning speed, the spin light should remain steady, and it should go on to the next step. So it did setting the default shim, and then it comes up here with the lock window. This is because we chose manual lock. Now I'm not going to go over manual locking. Normally you do not need to do manual locking, but if you do, contact Instrument Center staff and we can discuss how to do that. What locking is this is a measure of the deuterium NMR signal in the sample. So our solvent is deuterated, and what we're seeing here is it's transmitting constantly at a particular frequency that's been determined by what we put in here. It looks in a table and it picks a frequency that's correct for this instrument, and it transmits continuously at that frequency. This sweep back and forth here is sweeping the magnetic field up and down slightly. That's accomplished by means of a room temperature electromagnet that's inside of the superconducting magnet. So as it sweeps up and down, it goes through the deuterium NMR resonance. And so if you see where these two lines cross right here in the middle, that is the actual resonance frequency of the deuterium. So what we want to do when we lock is the instrument will look for this resonant condition, and then rather than sweeping the field up and down, it will hold it on resonance at that point. That will make sure that the magnetic field is stable over time. So especially for longer experiments, if the temperature or the pressure in the room were to change, that could cause the superconducting magnet drift to be different and cause the magnetic field to be slightly different. Or the frequency source could drift slightly. When it's locked, that doesn't matter because the two are linked together, and they'll compensate for each other. In this case, we're just going to do automatic lock. So I can just choose automatic here. And what you'll see is that as it sweeps back and forth, it's going to find that resonance, and it's going to jump up. And then it's going to go into a different mode where it's holding it on resonance. And now the line going back and forth doesn't indicate any sort of sweep. It's just a measure of the history of the lock signal over time. So if it's going up or down, that means the lock is not stable. Also, if you look at this, the signal to noise of this signal can give you an indication of how homogeneous your magnetic field is or how good your sample is for NMR. If the signal is very noisy, then there's a problem with your sample typically. Or if the signal's down on the bottom, then it didn't lock. And that could be that your sample is in the wrong position, or that your solvent is incorrect, or there's something else wrong with the instrument. In this case, it's fine. So we can go on to the next step, which is shimming. And again, we could do automatic. But if we wanted to do manual shimming, we could use this panel over here. And like I said, the main thing that we need to compensate for is the sample itself as it goes into the magnetic field. The rest of the field has been made as uniform as we can prior to you running your experiment. So we need to compensate only for your sample. Now we spin the sample, and the tube being very uniform helps compensate for any distortions that are perpendicular to the axis of the sample. But along the axis of the sample, we're not going to be able to predict what the field distortion is going to be, because the sample might be a slightly different height, might be a slightly different position, and the identity of the solvent might be different. All of those things will change how we need to compensate for its effect on the magnetic field, and that's going to be something we have to compensate on the instrument for each sample. So what we're going to do is to adjust the Z1 shim. This is a linear distortion of the magnetic field along the axis of the tube. That's why we call it Z. We can turn this knob and we can look for its effect on the magnetic field, on the lock signal here. Now the lock only has a signal where the deuterium is exactly on resonance. So if the signal is weaker, that means that only a small fraction of the sample is on resonance. If the signal is stronger, then a larger amount of the sample is on resonance. So as we turned it here and it got weaker, that meant that we're making the field less uniform. So I'm going to turn the knob the other way and try to make the field more uniform. And it's going to get better and better. If it goes off the top of the screen, then we can adjust the lock gain, which is another button here, and bring it down onto the screen. And then we can go back to adjusting the Z shim. And okay, we've passed the optimum. So you see, if it gets better and better, keep turning it the same way, it'll reach a maximum and then it'll start to get worse again. So we want to go back to that point where the lock signal is at a maximum. Once you've maximized it using the Z shim, you can go on to the Z squared shim and do the same procedure. So we'll try to make the lock signal as high as possible. At some point, it's going to stop improving. So we can go back to that maximum. If Z squared changes significantly, it's a good idea to go back to Z. And again, you can try to see if adjusting it will make the signal any better. In this case, it's about as good as we're going to do. So if you want, you could click Shim OK, and it would take these shim settings and run the spectrum. Now, the higher order shims, Z cubed, Z to the 4th, Z to the 5th, do make a difference on the sample, but they become increasingly difficult to adjust because, as you saw, to adjust Z squared, we had to go back and optimize Z again. To do Z cubed, the correct setting for Z cubed depends on Z and Z squared. So it's a very long iterative procedure to get to the optimal settings. This is one reason that the auto shim is a nice option, because the auto shim works in a completely different way. It takes an image of the sample, and from that image it can calculate analytically how to set the different order shims on the system. So when we click automatic, it's going to turn off the lock, and it's going to take two data sets on the lock sample. These are images. From these data sets, it's going to calculate the field profile, and then from that field profile, it's going to calculate how to set the shims. As the name implies, it's all automatic, so you can just sit back and watch it happen. Now, some limitations of the auto shim are that it assumes that the shims are linear, which means that if it puts twice as much current into the shim, that it will have twice as much effect. This is fairly true, but not completely true. And the closer it is to a good shim, the better that this auto shim works. So if you're really far away from a good shim, this process may need to be repeated multiple times. If you're very close to a good shim, it should, assuming the auto shim is working, only make it better. So if you want to get the best shims on the system, what you can do is you can do some manual shimming prior to running the auto shim. However, it should give you acceptable results just running the auto shim on its own. Okay, so now if we go back to Icon NMR, we can see that we've already done setup, locking, shimming. It did receiver gain adjustment, and now it says ZG in progress. That means that it's actually running the spectrum. While that's happening, we can look at this other window here. This window indicates how much time is remaining in the spectrum. If you want to look at the spectrum while it's running, you can click on this button here that says Spectrum. This will bring up a snapshot of the spectrum as it currently is. If you're happy with it as it currently is with the snapshot, which we'll see here in just a second, if you were happy with this, then what you could do is you could click Halt. You almost never want to click Stop, even though it's red and calling out to you. Stop will not do what you want. Halt will do what you want. Halt will wait to the next scan, save the data, and then move on to whatever is next in the list. What Stop will do is it will just stop. It won't save the data, it won't go on to the next thing, it'll just stop. So this is especially important if you're in a position where you need to halt somebody else's experiment. Be kind to them and halt their experiment, don't stop their experiment. Because if you stop it, they may lose all their data. So that's not a good thing to do. In this case, we'll wait for the experiment to finish, so the time remaining is done. If there was another thing in holder 1, it would immediately start that. There's not, so it goes and comes up with this window here that says click here to start eject routine. This is probably the biggest limitation of using the automation mode for manual spectroscopy. If it gets to the end of the list here, then it wants to eject your sample, and there's no easy way to cancel it at this point. So the lesson of that is if you want to run multiple things on a sample, you should set them all up in advance before it gets to the end of the list. Otherwise, you're going to have to do the setup again. In this case, we're done, so we can click OK. And we're going to get the dummy sample. And the depth gauge. We'll take out our sample and put back the dummy sample. Now, even though we're not going to take data on the dummy sample, it's important to put it at the proper height. The reason is if it's too far down, it could hit the bottom when it goes in and it could break. If it's too far up, it may not make a good air seal on the inside there, and then that's one of the main reasons that samples don't eject properly. So you want to make sure it's at the right height before you put it back, and you want to make sure that you put it back before you go on to the next step. So we're back here. We've put back our dummy sample. We've taken out our sample, so we can click OK. On the automatic sample changer, you can leave this window open, and you can use this change user button to change from one person to the next. If you're running manually, you should not leave this window open. The reason is that if you use the change user button, the next person will not be able to delete your experiment from the list, and eventually the list will get filled up. So that's not a good thing. So to be kind to the next person, you should not use this, and you should not leave this open. But what we should do is you should go back to the run, and you should click Stop Current Run. Yes, you really want to stop. And then you should go File, Close. That will bring back this green icon NMR window, and the next person can log in. Now, if you click Spectrum, your spectrum will be here. If you didn't, there may not be a spectrum here, but you can find it with the browser panel. Expand the list of users, go down, find your username, find today's experiment, double-click on your experiment, or you can drag it over into the window, and then you'll have your experiment. Now, we do most of our workup offline, but if you want to look at your data prior to going and working it up offline, a couple things you can do. You can use the ×2 and divide by 2 buttons to scale up and down the spectrum. You can use the mouse by clicking and dragging to zoom in on a region. You can use this outward-facing arrows to go back to a full spectrum. And you can close your spectrum without losing your data. It will still be there. If there's a whole lot of experiments open, which there may be if a lot of people are using the instrument, go ahead and close them, because too many of them might slow down the program. Okay, so we finished taking our data, we've put back the dummy sample, and we've left the instrument in a state that's ready for the next user. So we're finished.